description for design and calculation, and after for the code design, you should submit a part drawing and this description. And first, for the design, you should select of model. First, to choose the type of model, and usually choose 3-phase AC motor, especially the Y series. Okay, and if the system starts break frequently, such as hoisting equipment, you can choose YZ series or YZR series. Okay, usually choose Y series, and then you calculate the power of motor, and for the machine whose workload is stable and operation is continuous for a long time, the motor can be selected according to the rated power and the verifying of height, and the starting torque of the motor is not required, which it should satisfy that the rated power larger than the required power, and the required power can be calculated as below. And PW is the required effective power or Q of working part, and this is the total efficiency for motor to working part. It's equal to F times the times velocity and divided by this. And for different special machines, the calculation of PW is different. For better conveyor, the required power can be calculated by this. Okay, this is not okay by this to the 10th. Okay, the 6th power, and D is the diameter and N is the speed, and the total efficiency is determined by the yeah.
Please, I think fast. Right.
Yeah. What's wrong?
I think you are talking too fast. It's hard to catch up with you. Maybe you can calculate more slow.
Oh, sorry, I can't hear you.
你说快了，可以说慢慢的。
Okay. Okay.
Ali, your microphone is. I can't hear you.
You can't hear me?
No. Laushi, you is okay.
Okay. And the total efficiency can be calculated by this. N1, N2, and NW are the efficiencies of kinematic pairs or transmission pairs, such as coupling, gear, belt, bearing, and roller. And you can obtain the the efficiency from the table, from this table. I have sent this word. I have sent this word to the group, so you can find be quiet, sorry.
Please, can you mute your mic, bro? Why? Hello?
Don't worry, I muted it.
Okay. From this this word, you can find the design date. This table, you can find the efficiency for transmission part. For example, for gear, according to its grade accuracy grade, you can find the efficiency, and this is the transmission ratio rate, and this for belt. For belt, the efficiency is 0.95, and the transmission ratio usually within the range from 2 to 4, and this is for chain, and this for bearings and the couplings and roller. Then you can find the transmission part, the efficiency, and then to calculate the total efficiency, okay, and then determine the rotating speed of motor, and when after the capacity and type have been selected,
老师
yeah,
老师 I didn't understand the first 2 pages. It was too fast. 太快了，你可以慢慢吧。
okay, sorry. And first to calculate when per minute. So when we choose the motor type, we suggest the 2 speeds. And for example, there is a belt conveyor as shown in this figure. This is the motor. Okay, this is the motor, and this is the working part. And this is a roller, and this is a belt driver, okay, belt, and this reducer. In the reducer, there are 2 pairs of gears, okay, and this means the bearing,
Jeff?
the bearing support the gear, okay. There is this symbol. This symbol means the bearing, okay,
Okay.
bearing, and this is a bearing 2, bearing, okay, be quiet, and this is a coupling. This is a coupling, okay, this is a coupling. So from the motor to the working part, from the motor to the working part, oh, be quiet, okay, be quiet.
Saleh, can you please mute them?
Okay, from the motor to the working part, there are belt, okay, belt, gears, and bearings and coupling. So the total efficiency, we should consider the efficiency of belt, gears, bearings, coupling, and the working part, the roller. Okay. So in this finger, it's peripheral force or tangential force F, and the linear velocity V, and the diameter of the roller are respectively 600 and 0.5 and 300 millimeter. So we lose the force, the V, and the diameter for the working part. And the load is stable, and the operation is continuous. Working condition is dusty, and the power is 3-phase AC, whose voltage is 318 voltage. Then please select a suitable motor and then choose the type. Choose the type. Univarni, we choose Y series motor. Okay, Univarni, we choose Y series motor, and then to select the power for Y series motor, the required effective power of the working part, the roller, can be calculated by this equation. F is the force, V is the linear speed, okay? And then we can calculate the required power of the roller. F, we lose the F and the V, okay? And then we calculate PW, and then we should calculate the required power for the motor. Then we need to calculate the total efficiency. Okay, the total efficiency, we lose the required power of the working part. Then we should calculate the required power of the motor. So we should consider the efficiency of belt, gears, bearings, coupling, and roller, and then the total efficiency can be calculated by the efficiency of belt times the efficiency of gears square and efficiency of bearings to the horsepower, and times the efficiency of coupling, and times the efficiency of the roller, because there are 2 pairs of gears and 4 pairs of bearings. 1, 2, 3, 4. 4 pairs of bearings and 1 coupling and 1 roller and 1 belt. So the total efficiency can be calculated by this. Okay, any question? This is for the total efficiency, and then we need to determine the
Okay.
efficiency. Yeah.
Can you say it again? The belt, gear, bearing, and coupling. Can you calculate?
Okay. So from the motor to the working part, okay,
Okay.
we should consider the efficiency of transmission parts, okay, from motor to the working part. So we should consider the efficiency, And then we should determine the efficiency of belt, gear, bearing, coupling, and the roller. Okay, and then from
No, Christian.
what?
I didn't understand well the way you counted. Like, can you count by marking, by putting something so that we can see?
You can see
Yes.
which.
Yeah, like
Uh,
count by putting something.
you can't. This you can't understand.
Yeah,
Like
Lausi,
how we
let me
counted.
help him. Bob.
Mm.
This is
This one is built.
okay.
Did you get it?
Okay. This is the
Mm.
this is the motto. Okay.
Okay, Lausi, do it.
Yeah,
This is a motto, and this is the motor shaft.
yeah.
Okay. The determine the efficiency of the component. For example, the you can obtain from this table. Okay. From this table, for example, for example, and the belt, the belt, when you choose the efficiency of the belt, you should choose a accuracy grade first. Okay, you should choose a grade first. And in this example, it's choosing the line grade. So the efficiency is 0.96. It's 0.96. Oh, no. Oh, for the gear. Oh, this is for the belt. For the belt is 0.95. So in this, there is a little wrong. The belt should be line 5. Okay. And for the gear, choose 8 grade is 0.97. Okay. For the gear. And for the bearing, for the bearings, if you choose ball bearing, it's 0.99. If you choose roller bearing, it's 0.98. Okay, so there it choose the bearing, it's 0.99. And for the coupling, gear coupling is 0.99. Okay, and then for the roller, it's 0.96. So we lose the efficiency of transmission parts, and then we calculate the total efficiency. And then calculate the required power for the motor. It's the required power of the working part divided by the total efficiency. So we calculate PR. PR is 3.64 kilowatt. Okay, any problem? Any problem?
No, Lausi, it's all right.
Okay. Okay, and then we calculate the total efficiency first, and then to calculate the required power of the motor. And then we choose.
Lashe,
Yeah,
Lashe, the PW, how did
yeah.
you get 3? PW.
What's problem?
PW, how did you get 3?
Okay, PW. How to get the PW? The required power. Use this to calculate the required power for the working part is F times the V. Okay.
Lashe, what is the V, please? F is the force,
V.
right?
Yes, F is the force. V is the linear velocity.
Okay. Thank you.
Okay, okay. Total type according to its required power.
Oh,
Okay, and
yeah.
then from the table, 19 to 1, you also can find in this word. Okay, in the design date word. Okay, and this is the table 19 to 1, and for the motor Y series 3-phase motor. Okay, and this is the synchronous speed. Do you remember? Usually there are four synchronous speed. The 3,000 and 1,500 and 1,750. Usually, we choose the speed with 1,500 or 1,000 revolute per minute. Do you remember? We usually choose the two synchronous speed with 1,500 or 1,000. And then this is the rated power. And we know that the rated power should be larger than the required power. So we should select the type with the rated power larger than the required power. The required power for the motor is 3.64. Okay? So should be larger than 3.64 if we choose the speed, the synchronous speed is 1,500. We can choose this type. Okay? Okay.
Okay, 老师。
You can choose this type because its rated power is 4, is larger than the required power. And if we choose the synchronous speed is 1,000, we can choose this type. For this type, the rated power is 4 kilowatt 2. Okay?
Yeah.
So we have
Lakshmi,
two.
I have a question.
Yeah.
We can select the synchronous speed of 1,500 revolution per minute or 1,000 revolution per minute. So we'll
Yeah.
write the two answer or just write one, mentioning that it is, suppose it is 1,000 revolution per minute.
Usually you choose the synchronous speed with 1,500 or 1,000.
Okay. But at the time of writing the answer, we'll just select one or two.
Okay, you'd better choose two and compare the two selection.
Okay, Lakshmi.
And then for the synchronous speed with 1,500, we choose this type with the rated power is 4 kilowatt, or choose this type with the rated power is 4 kilowatt 2, and then we determine the rotating speed. The rotating speed of the roller we can calculate the rotating speed of the roller. Use this equation. We lose the linear velocity v, okay? And we lose the diameter of the roller d. And then we calculate the rotating speed of the roller is 31.8 revolution per minute, okay? Okay, and then we select two plane for the motor type, okay? In this table, this is the type Y112M4, and this is the type of the motor Y132M126, and the rated power is the same, and the synchronous speed is different. For this type, the speed is 1,500, and for this type, the speed is 1,000. And then the speed with full load. This value can be obtained from the table, okay? This is the speed. For this type, the speed is 1,440, and for this type, the speed is 960. Okay, and this is the speed with full load for the two plane. So we can calculate the total speed ratio from the motor to the working part, from the motor to the roller. So if we choose this type motor, the speed ratio is 1,414 divided by this. So the total speed ratio, yeah.
What's the difference between this synchronous speed and speed with full load? This one
Okay.
and this one.
Okay. Okay. This one, the synchronous speed is the rotation speed of the magnetic field of the motor. It's usually larger than the speed with full load. This is the rated speed, usually the rated speed, and it's the speed under nominal voltage and rated frequency and rated load, and the speed with full load is equal to the synchronous speed times efficiency, and the efficiency is less than 1. Okay.
Mhm.
And this is the speed of the magnetic field. Okay.
So is it means like we can say this one, this speed with full load, it's an real speed, and the other one is like calculated speed.
Yeah, this is you can consider it as the rated speed, okay, and with full load, and then you calculate the speed ratio, the speed ratio from the motor to the working part. For this type, it's 1,440 divided by the speed of the roller is 31.8. So the total speed ratio is 45.28. And for the plane 2, we choose this type motor. The speed with full load is 960. Okay, and then we calculate the total speed ratio is 30.19. So the total speed ratio, compare the total speed ratio, we know that this is less than this. Play 2 is less than play 1. Okay. So we choose play 2. Play 2 because if we choose play 1, the speed ratio is too large. It's too large. Okay? It's too large. So we choose play 2. So we choose
what
this
problem
type.
with speed ratio is too large?
Okay, this total speed ratio is too large from motor to the rotating speed. And in there, how to obtain the motor, the the motor, the speed of the motor is 1,440, and the speed of the roller is 31.8. Okay, so we should use the belt and the gears to decrease the speed. Okay,
Yeah.
so for belt and the gears, for the belt, it has a speed ratio, and the gears has a speed ratio. If we choose play 1, the speed ratio is too large. It's too large. Speed ratio I is equal to J2 divided by J1. Do you remember?
Yeah.
For belt and gears, I is equal to J2 divided by J1, and J is the teeth of the gears or the pulleys.
Yeah.
So if the speed ratio is too large, and then the driven pulley or the driven gear should be larger. Okay. Okay. So the J2 should be larger with play 1 because the speed ratio is larger. Okay. So usually we choose the plane with small total speed ratio. So we choose this type. Okay.
But how you got this rotating speed of roller? 60 V divided by pi d.
Okay. We use this. This is the linear velocity. The linear velocity divided by pi d is the circumference.
What is d?
D is the diameter of the roller.
All right.
Diameter of the roller. Okay. And calculate this, and to calculate the total speed ratio, and then we choose this type. Okay.
So is this formula is universal formula? We can use it in everywhere.
Yes. Yeah. It's a formula. It's a formula for the roller. You can use this to calculate the rotating speed of the roller. This is the formula. Okay.
What is the relation with this 60?
Which?
60 V divided by pi d.
Okay. This is because V.
I think it's a formula.
Yes. The V is the linear speed. Okay. V is the linear speed. The linear speed is 0.5 meter per second. we should transfer second to minute. So
Oh,
we
that's why it's
times
60.
so
Mhm.
we times 60.
All
Okay.
right. Yes, Lucy. Understand.
Okay.
Thank you.
And then we choose this. And then we need to distribution the speed ratio. So let's have a break for 10 minutes, okay?
All right, Lucy.
Okay, have a break.
老师
Distribute the speed ratio to the transmission component. And according to the motor speed with full load and the speed working part, we calculate the total speed ratio, and then the total speed ratio should be distributed reasonably to each level. And we should consider that first, the speed ratio, the speed ratio of each level should be in rational range to compact structure and visualize process, and and recovered speed ratio are shown in table 10:1. And the size and structure of different levels should be considered and determined reasonably. For example, the speed
Lovely.
ratio. Yeah.
I have a question. You have written that the I should be distributed reasonably to each level. The level
Yes.
is from motor to belt and from belt to gear. These are the levels.
Each lever include the belt and the gears. Okay.
Oh,
The
lovely,
belt
got it.
of the and the gears. And for example, the speed ratio of belt driver should not be too large and should satisfy that the speed ratio of belt should less than the speed ratio of gear. And each transmission part should not interference with each other. When the mating materials of two levels are the same and the two phase wind factor are the same, the constant vertical strength should be made approximately equal. And the distribution of speed ratio can be done according this. I1 and 2 means the speed ratio of high speed level and low speed level respectively, and I reducer is the speed ratio of the reducer. Okay. And let's say the example. The data are the same with the example 1, and the total speed ratio is 30.19, and please distributing the speed ratio. First, according to the table, we choose the speed ratio of the belt from this table. We find the belt transmission. For the belt transmission, then recommended transmission ratio or speed ratio is within the range from 2 to 4. From 2 to 4. So we choose the value of the speed ratio of belt first. You can choose the value within this range. In there, we choose the speed ratio of the belt is 2.5. Okay, it's 2.5. And this is the speed ratio of the belt. And then we calculate the speed ratio of the reducer. The speed ratio of the reducer is the total speed ratio divided the speed ratio of the belt. Okay, the total speed ratio from motor to roller is achieved by the belt and the gears. Okay, and then we select the speed ratio of belt at 2.5. And then we calculate the speed ratio of the reducer. It's the total speed ratio divided by the speed ratio of the belt. This is the total speed ratio, and this is the speed ratio of belt. And then we calculate the speed ratio of the reducer is 12.076. And then we distribute the speed ratio within the reducer.
Laushi,
The speed ratio, yeah.
we can take any value from 2 to 4. Here you have taken 2.5 as the speed ratio.
Yes, you can choose from the range 2 to 4. You also can choose 3. You also can choose 2.8. Okay? You
Yes,
also can
Laushi.
choose 3.5 within the range from 2 to 4. Just okay. Okay? And then the speed ratio of high speed level for 2 level gear reducer is that I1 is the speed ratio of this pair of gears, and we use this equation to calculate. It's a square root 1.35 times the speed ratio of reducer, and then we calculate the speed ratio of I1. I1 means the speed ratio of this pair of gears. Okay, and then we calculate I2 is the speed ratio of this pair of gears, and it's the speed ratio of reducer divided by I1. And then we distribute the speed ratio for the belt is 2.5. For this pair of gears, it's 4.038. And for this pair of gears, it's 2.989. Okay, we distribute the total speed ratio first to choose the speed ratio of belt, and then use this equation to calculate the speed ratio I1, and then to calculate speed ratio I2. Okay, any problem? Any problem?
No problem.
Okay, and then we distribute the speed ratio, and then we should calculate of kinetic and dynamic parameters. First, according to speed with full load of the motor and speed ratio, rotating speed of each shaft can be calculated. And two, the power and torque of each shaft should be calculated according to the input. There are two methods, and after determining motor and the distribution of speed ratio, the transmitted power, rotating speed, and torque of each shaft can be calculated, provide the basis for the design and calculation of transmission components of shaft. Each shaft from high speed to low speed is defined as shaft 1, shaft 2, respectively. The speed ratio and efficiency of two adjacent shafts are respectively I12, I23, and this is for efficiency. And input power of each shaft is P1, P2, and rotating speed is N1, N2. Input torque is T1, T2. So we have this. We have these equations, and P0 is the output power of motor, N0 is speed with full load of motor, and T0 is output torque of motor. Okay, and P1 is the input power. P1 is input power for shaft 1. Okay, and I01 is the speed ratio from motor shaft to shaft 1, and this is the efficiency from motor shaft to shaft 1. So it's difficult to understand. So we we look at the example. The date are the same with example 1, and please calculate the kinematic and dynamic parameters of each shaft. And for P0 is the output power of motor. Okay, P0 is the output power of motor. So P0 is the required power of the motor. We have calculated before. Use the PR. Where is the PR? Calculate PR. There. Okay. PR is the required power of the working part divided by the total efficiency. Okay. PR is the P0. Okay. And N0 is the speed with full load of motor. From the table, we can obtain the N0. We choose the plane 2. For plane 2, the speed with full load is 916 revolute per minute. And then we calculate the T0. T0 is the output torque of motor, and T0, we use this equation to calculate. It's 9.55 times P0 and divided by N0. So this is for shaft 0. Shaft 0 is the motor shaft. Okay. And then for shaft 1, okay. This is the shaft 0, okay? And then we should calculate the input power and torque and rotating speed for shaft 1. This is shaft 1, okay? Okay. And
Yes.
for shaft one, it's the output power of the motor times the efficiency of the belt. Okay, times the efficiency of the belt. This times the efficiency of the belt, and the efficiency of the belt is 0.96. Usually we choose the efficiency of belt as 0.95, and then we calculate the input power for shaft one is 3.49. Okay, and then we calculate the speed ratio of shaft one. It's the speed ratio of motor shaft divided by the speed ratio of belt. We choose the speed ratio of belt is 2.5, and the rotating speed of the motor shaft is 916, and then the rotating speed for shaft one is 384 revolution per minute, and then the input torque for shaft one, we can use this to calculate. Okay, we lost P1 and N1. We use this to calculate the input torque for shaft one. And for shaft two, this shaft, okay? For this shaft, the input torque, how to calculate the input torque for this shaft, we should consider the efficiency of gears and the bearing, okay? For P1 is the input power. And then for the input power for shaft 2, we should consider the efficiency of gear and bearing. So P2 is P1 times the efficiency of gear and times the efficiency of bearing. And we lost that the efficiency of gear is 0.97 and efficiency of bearing is 0.99. And so P2 is 3.35. And then the speed ratio, the speed of N1 is N2 is N1 divided by the speed ratio I12 or I1. We have calculated I1 is 4.038. So N2 is N1 divided by the speed ratio I1 or I12. And then we lost P2 and N2. We calculate the input torque for shaft 2. And then for shaft 3, we also need to consider the efficiency of gear and bearing. So P3 is P2 times the efficiency of gear and times the efficiency of bearing. Okay, and N3 is N2 divided by the speed ratio I2 or I23, and the speed ratio I2 is 2.989. So we calculate N3 and then we calculate the input torque of shaft 3. And then for shaft 4, for this shaft, we should consider the efficiency of the input power, we should consider the efficiency of bearing and coupling. So P4 is P3 times the efficiency of coupling and times the efficiency of bearing, and M4 is equal to N3. The rotating speed of shaft 4 is equal to speed of shaft 3. And then we calculate the input torque for shaft 4, T4, okay? And this is to calculate the input torque and power and the rotate speed for each shaft, okay? And determination of transmission scheme should consider this belt drive is kind of friction drive. Its transmission is sturdy and it can absorb quite a large amount of sudden shock, but its transmission ratio is less constant or exact. And while transmitting the same torque, the structure size of the belt driver is bigger than that of other form of transmission. So belt should be placed at high speed transmission. 2. The operation of chain driver depends on the meshing of chain and sprockets, and its average transmission ratio can keep constant. Moreover, chain drive can operate under an adverse working environment, but the instantaneous velocity of the chain is not constant, leading to impact. So generally, chain drives are used at a low speed level, and the open gearing should be arranged at low speed level because of its poor working condition. And usually, helical gear is used in multi-stage gear drive because its stability is better than sport gear. So in our course design, we usually choose helical gear. This is a design case as shown in the figure. The reducer is required. The reducer is required to working continuous without reverse under stable load and clean environment for 8 years. The power of the working part is 1.95 kilowatt, and the speed of the working part is 60 revolute per minute. So we lose the power and the speed of the working part. Okay, and then first we should choose the type of the motor, and we should calculate the total speed ratio and then distribute the speed ratio, and then we should calculate the input torque and power for each shaft and calculate the rotating speed of each shaft. This finger is different from this finger in our exams, okay? And in this finger, we note that from motor to working part, there are coupling, bearing, gear pairs, and coupling, bearing, and this is helical gears, and this is a pair of bevel gears and coupling. and then the working part. Okay. So first we choose the type of the motor, and from we just load that the power of working part and the speed of the working part. Okay. And first select and calculation of motor. Usually we choose Y series. Okay. The power of working part. We have lost the okay. No. There is a need. Okay, this is oh no. No. Wrong. Working part. We lost the